Thank you. So I'd like to talk about, I would talk about mainly experimental results obtained at Tohoku University from the collaborative research results, which Professor Takahashi presented in the previous presentation. So I would like to explain about the background briefly. We performed the collaborative research project from 2015, October 2015 to October 2017 for 2 years. And the objective of this project is to convince many people that the anomalous excess heat phenomena is real. So we gather at Technova and Nagoya University, and 6 parties gathered, and we check our data, experimental data, from each other, and we get the results. So this figure shows a summary of our collaborative experiments. So this column shows praise for the experiments, and the next column is the sample name and the composition, like this. We made the experiment mainly using melt spinning material, but as Professor Takahashi stated, nanopalladium only sample give us no excess heat. But except these 3, we get excess heat, significant excess heat. And this one is a gas, type of gas. We use deuterium or hydrogen, depending on the material. And this column shows released enthalpy, released energy obtained by these 16 experiments. So we can see that about megajoule per mole D or mole H energy we get. And especially this one is a very large one. The other experiment usually few megajoule or 10 megajoule, like that. So okay, so next one. This figure shows summarized obtained energy level. This blue region belongs to the chemical reaction. So this one is released energy per fuel, per hydrogen, or uranium. In the case of nuclear reaction, of course, we have a very large value. And based on our experimental results, we can draw these areas we get. So our data obtained excess energy cannot be explained by known chemical reaction. That's a very important point. Okay, so I will explain about our experimental setup, mainly at Tohoku University. Essentially, this experimental setup is similar to the Kobe University's. We have a reaction chamber in the center of this chamber, and this reaction chamber have 500 cc. The volume of the reaction chamber is 500 cc. And we have samples here, samples in the reaction chamber. And also we have a heater surround the reaction chamber and the center in the chamber to activate the sample. And we estimate the excess heat from this reaction chamber by oil flow calorimetry. So we can estimate the temperature difference and the flow rate, and we can estimate the excess heat from the reaction chamber. And the outer region of the reaction chamber is evacuated to avoid the convection, to avoid the heat transfer by convection. And also, this large chamber is located in the static chamber. I'll show you. This is the figure. This one is a chamber, and in this, there's a reaction chamber in this chamber. And we have a flow pump and hydrogen reservoir, and all the experimental setup in the static chamber, thermostatic chamber, okay. And this figure shows the sample preparation by melt spinning. Melt spinning, at first we melt metal, and the metal is quenched very rapidly, by rotating large disk, copper disk, and we get the amorphous metal tape. And we cut the metal tape and oxidation to formation of nanoparticles. And sometimes we perform the experiments using the same sample. One is at Kobe University and one is in Tohoku University. Okay. So this figure shows nanoparticle, loading of nanoparticle. We have 1 millimeter zirconia beads as a filler, a dummy in the reaction chamber, and we put the nanometal sample like this. Okay. And excess heat evaluation is like this. We can measure the flow rate and density and specific heat and the delta T, and eta is recovery rate. The recovery rate is estimated by based on the Planck round. Okay. And this one is an error estimation. Error factors for excess heat evaluation, mainly fluctuation of oil flow, and the other temperature fluctuation and fluctuation of power input. In the case of CNZ5, we have about 0.3 watt or 0.75 watt error. Okay. Okay, so I like to move on to the experimental results. Two parts. First part is a repeated experiments using some same composition samples at Tohoku University. And the second one is replication experiments using same samples at Tohoku and Kobe universities at different places. Okay. So first part, replicated experiments using same composition at Tohoku University. In this case, we use a copper nickel zirconia type sample with hydrogen gas. Okay. So this is a summary of repeated experiments using copper nickel zirconia OX with hydrogen gas. we perform 3 experiments using same composition sample. First one is CNZ5S. This case is already reported at ICCF-21. And this one is done in 2016. And second one is done 2017. And the last one is very recently performed experiment. CNZ5S and CNZ6S and CNZ5S-R. R means re-oxidized sample, same one. Okay, so this column shows the temperature of reaction chamber. And these obtained maximum power. And the released energy, enthalpy, is here. As you can see, that we can get few megajoule per mole hydrogen. And this one is 68 electron volt by hydrogen and 55 electron by hydrogen. So as I said, we cannot explain these energy by known chemical reactions. And feature of these 3 experiments is a coincident burst-like coincident increase of pressure of the reaction chamber and gas temperature, as I explain later. So at first, I will show you the excess heat generation results. Okay, this one is already presented at ICCF-20, but again, first time experiment, we can see that the excess heat beyond LR, significant excess heat, and in this case, these values obtained. And also, in this case, and also for other case, we check the consistency of the excess heat result, comparing the thermocouples measured data. We have many thermocouples in the reaction chamber and the outer reaction chamber, and so we make sure that this excess heat from this excess heat is consistent with the measurement result of many measured point. Okay. Second time excess heat result. Excess power is not so high, but lasting very long time, for a long time. So we got a very large energy value. And third time, a recent experiment, we get these data. So excess power increasing like this. Okay, so I would like to explain about the next point. Burst-like coincident increases events of chamber pressure and upper side temperature. We have a sample here. This figure shows the cross-sectional view of reaction chamber. And we have a sample here. And this red point shows the pressure in the reaction chamber. This reaction chamber is connected to the hydrogen reservoir. So, we observed this kind of pressure rapid increase. And coincidentally, we measure the E2 pipe temperature increase. So in the case of pressure, in this case, 0.52 increase up 0.53 or 4, it's a significant increase. And the temperature correspondingly about 5 degrees. So it's not a noise. So these data reproduce second time. In this case, increase of pressure and the temperature increase is a little bit smaller, but coincidentally, Bath-like event we observed. And third time, recently, also we observed these phenomena. Red line means pressure, and E2 is a pipe temperature. This one is correspond to the gas temperature. So we suspect that the high temperature H2 gas rushed to the reservoir in this case. Okay, so if we look at closely this burst phenomena, this one is pressure and temperature, and 1 point is correspond for 1 sec. 1 point is 1 sec. So you can see at this point, pressure increase up about 1 second or 2 seconds increase up, and correspondingly, temperature is increased up. But the temperature response is 4 or 5 seconds. It's very reasonable if we assume that the very high hydrogen gas goes through the top of the chamber. So, and another evidence I show you. So this figure shows the broken zirconia beads after excess heat reaction. This one is a second case, second experiment results. First experiment results. As I said, we have about a 100 gram sample and 1,030 gram zirconia beads. The sample was received after the experiment from zirconia beads, but we found that some broken parts of zirconia beads were mixed with metal nanocomposite sample. As you know very well, zirconia beads is very hard, so it is not so easy to break. So it suggests that very large local thermal stress was loaded on the zirconia beads, I think. Okay. And also another evidence of burst phenomena. This is the second experiment data. Photo of the upper flange after CNZ6S experiment. Upper flange is here, located here. Upper flange is here. And we have a sample, and beads is here. And after experiment, we open the flange, reaction chamber. So we found something adhered to the upper flange. This region, something adhered, you can see. So we suspected, we thought that some samples sprout out to the upper chamber. So to verify, we solved these areas by HNO3 and performed ICP mass analysis, and detected elements are consisted of copper, nickel, and zirconia. These are the sample. So we can see that the sample sprout out to the top of the flange. So, okay, so I will show you the ICP mass results. And this is the results of adhered material, CNZ6. Mass range is for this case 50 to 73.5. And red point correspond to the CNZ6X sample. And black and blue correspond to the blank HNO3, different blank. So you can see that nickel and copper is the main element, and a little bit stainless steel composition. And the higher region, we also detected zirconium like this, and plus stainless steel composition. Okay. Let's move on to the next point. Lubrication experiments using same sample at Tohoku and Kobe University. In this case, we explained about P and Z type, palladium, nickel, zirconia type with D2 gas. This results show the comparison of excess heat at Kobe and Tohoku at room temperature. So as you can see, red line means is Kobe and the blue line is Tohoku. Very similar behavior, and also released energy is very similar. So we can check that our measurement system is doing very well, very well. And this figure shows comparison of the excess heat between Kobe and Tohoku at elevated temperature. Very large excess heat obtained at elevated temperature. So red line means Kobe, and the blue line Tohoku. And we compare the nearly room temperature comparison excess heat between Kobe and Tohoku at similar temperatures, because temperature in the reaction chamber is very important for excess heat and excess heat generation. So we can see that the same level excess power is obtained. Okay, so I would like to conclude. Collaborative research project between 6 parties on anomalous heat effects were done from October 2015 to October 2017. Anomalous heat generation were observed for all the samples at elevated temperature, except for the palladium nano particles only. Integrated excess heat reached more than several megajoule by mole hydrogen or more mole deuterium, which could not be explained by any known chemical process. A coincident burst-like increased events of the pressure of reaction chamber and gas temperature, which suggested sudden energy release in the reaction chamber, were observed many times for an experiment using copper, nickel, zirconia, C and Z type sample with H2 gas. These burst-like events were replicated twice, and experimental evidences that suggest very large local heat release were obtained. And qualitative reproducibility between Kobe and the Tohoku experiments was very good. And I'd like to acknowledge these people. Thank you very much.
Papers open for questions or discussion.
Hi, I'm Nicolas Chauvin, LENR Car, Switzerland. The burst-like events are really interesting, and I wonder if you have more information on the stress on the zirconia, this picture.
Yeah.
Because zirconia is extremely transparent. It's above, the transmittance is above 80% between visible light at the border of UV at 300 nanometer, down to 6 micron at mid-infrared. and there's no absorption. It's transparent over the entire range. And if you want to have a fast stress on the zirconia bead, you probably need to have also radiation effect, not just conduction. And it would mean that the temperature of your event goes in far infrared, which would mean that the temperature locally is higher than probably higher than 500 degrees C. So to be able to break those beads, so that would be interesting to understand better what is the thermal stress process to be able to break that.
Thank you. Very useful comment. I would like to estimate by stress level and also other method. So thank you very much for your comment. Okay, thank you.
Thanks very much. That was really interesting. I had a question about the pulses, the energy release pulses that came through. Looking at the data on the screen, it appeared that a lot of those pulses were reasonably similar in size. And I was just wondering whether you'd had some time to look at, I guess, the size, or there you go, you can sort of see it, the size of those pulses and estimating the energy around those pulses. Because usually when we think about these sort of reactions, we sort of think about them being more random. You know, one will be big, one will be small, and that sort of stuff. But there's obviously something really interesting going on with the idea that those pulses are all quite of a similar size. And I'm just wondering whether you had any thoughts around, you know, possible mechanisms for the pulses.
Yeah. I also noticed the same level of pulses, and I would like to analyze these strange phenomena more and more. So, thank you.
I had the same thought about radiation embrittlement of the zirconium oxide, which could cause the breakup of it. Second question, though, in general is, what's the triggering event? Is it just a certain temperature? And because your graphs show it happening and then stopping and then happening again, is there a triggering event that you see?
Trigger.
Yes, for the initiation of the event.
Yeah. I also noticed, and I'm thinking, but at this point we cannot definite answer. But these results are obtained the same condition. We usually put heater input is the same. Heater W1 round heater power input 134 and W2 0 in this case. And also for 3 cases, same condition. So, but at present, we can say that the same condition, we get the same phenomena, but trigger is a very difficult problem.
The other question is the triggering associated with absorption of hydrogen that you add to the system as time goes by?
Yeah.
Or do you have a fixed quantity of hydrogen to start with and don't add anything?
Yeah, thank you. Thank you.
You may have just answered my first question. Is the protocol that you put gas in, the gas is fixed? In previous years, there were descriptions of putting gas in, taking the gas out, putting the gas back in. But these days, it's you put the gas in the beginning, and then you let the thing sit and do its thing.
At first, usually we put the sample, and we evacuate, and we put the hydrogen gas or deuterium gas at room temperature. And after that, we switch on the heater, and we increase up the temperature, and we get these data.
Okay, if so, it looks to me like you don't have a whole lot of thermal insulation. If you were to, I mean, since this seems like a relatively simple type of experiment, you could imagine a different version of it where you had your chamber and your heaters and you had good thermal insulation around. It would seem to me you wouldn't need very many watts
So you
at all
are
to,
talking about some insurance of our system is not necessary. Your point is this region summer insurance.
I guess I'm thinking of a different type of experiment to try to maximize the excess power over the input power.
Yes.
I'm imagining for less than 10 watts, you could sustain this thing at 400 C or 350 C or so. And if you got a 10 or more watt output, then you're...
Okay.
Thank you, Dr. Iwamura. This is a really impressive collaboration, and I want to thank all of your colleagues, the various universities and companies that are putting this coordinated effort in. It's really important for our field. I don't want to put you on the spot, but I noticed that your funding stated that it ended in November of 2017, if I saw that correctly. Is it okay to assume that your research is continuing in this collaboration and that you have sustained funding?
We hope continue this project, but at this stage we cannot get the next larger funding. So we are now consulting each other to get the research fund from Japanese government.
Could you go back to the slide where it showed the isotopic ratios of nickel on the accretion on the underside of your DOR?
ICP mass results?
Yeah.
Right?
There.
Okay.
Am I reading this right? Maybe other people have got better eyes in the room. Would it appear that the 61 ratio there is lower than the 64 ratio?
So you were saying about this isotope ratio.
Yeah.
But in this case, usually metal forms nickel, hydrogen, or something like the hydrogen. So maybe it's difficult to say that based on this data, isotope ratio is different. But
well, it's interesting because what I see there is your 61 is lower than 64, but the natural isotopic ratio is reversed. And
maybe
this would look one of the most